Hi everybody, so in this video I'm going to show you how to find a pressure at depth H. Okay, so pressure at the depth. So let's consider a container and let's fill this with water. Okay, up to this label here. Okay, this is a picture of my dash is water really. I'm gonna tell so this water has a density rho. I can just write anywhere here, so I'm gonna write this here, rho density. Okay, now we want to find what's the pressure. Maybe if you want to find somewhere around here, let's say at this point. Okay, so what's the pressure there? So what we are going to do here is this. Before I start deriving, I want to tell you guys this. We will divide this water here. We will take a column of water from this container, and then this and then important thing here is this fluid is at rest. It's not moving, right? So this is a case of a hydrostatic fluid. Okay, so this fluid is at rest. What we are going to do after that is we are going to apply Newton's second law and then just find out what's the net force. Okay, and then by doing that we'll eventually come to the equation where we can find the pressure at depth. Now to do that, let's take a column of water here, this column here, and this is really a cylinder. Okay, so I know it's kind of looks like a rectangle, but I'm just drawing it. It's cylinder here. Let's say it has surface area. It's kind of like this, guys. Cylinder, right, like this, and then this has a surface area, top, this cross-sectional area A, and then this has a height H here. Okay, now you see there is a fluid on this side here on the bottom, no fluid on the top, so there is just maybe air or something, it's pressing down. Okay, so there is a pressure due to some sort of fluid here on the top, air or something like that. Let's say on the top it has some pressure P naught at this point here. Okay, I'm just writing this arrow to point here. Something is pushing it downward really, maybe. Okay, let me change that arrow here. If it makes easier for you guys, I'm gonna just make it like this, P naught. Okay, so this this P naught is pressing it downward to this column. Now this column of water also has what? Mass, which means, and it's if it has a mass, it must be affected by the gravitational force, so it must have some weight. So there is a weight force, right? But then there is also fluid here at the bottom also. That fluid must be pushing this column upward. So let's say it should be pushing it like this, upward. Let's call that pressure as P. Okay, at the bottom. Now you see there is also actually this fluid, they are pushing on this column. So if it's like this, it pushing here like this, they kind of cancel each other. Okay, if they are pushing from from two different opposite directions, so we'll ignore what's happening in the horizontal side because it's a net force is 0. So now let's apply Newton's law. From Newton's law, Newton's law, we can write F net equal to 0. This is just for this direction. Okay, so vertical direction. So the net force, what's the force here on the top? That's due to P naught, right? So let's say that pressure P naught can be written as what? P naught could be written as what? Force on the top. Let's write F top by cross-sectional area A, right? Same way we can also say at the bottom we have pressure P equal to what? F bottom by area A. Okay, and then this one has also weight. So the net force is, we have two forces that are pointing downward. This P naught pointing downward, the weight force also pointing downward, but this force from the bottom is pointing pointing upward. So we are going to write this down here. F top plus weight force. This weight is really a weight for, let's call, weight of this column, like mass of the column, right? Weight, gravitational force acting on the mass of this column of water. That minus this F bottom, right? This must be equal to 0. So now F top is what? We can just write this F top as P naught times A. So we get P naught times A plus weight force is what? Mass. Let's say this as mass M, okay? Mass times gravity minus F bottom is what? P times A, which is equal to 0. Now guys, remember we said this guy has the density rho. This fluid also has the density rho, okay? So I'm going to show you something here real quick here. So density rho equal to what? Mass by volume. How can we write this mass in terms of volume? Can we write M equal to rho times V, which is what? Rho V is what? Volume of this column. So really look at when we are talking about volume, we are talking about this entire volume. How can we find? If you multiply this cross-sectional area with the height, we get the entire volume. So we can write what? Area times H, okay? In place of volume, we are replacing by area times H. So we are going to replace in our equation also. So P naught A plus, in place of mass, we are going to write rho A times H times G. G is from here, minus P times A equal to 0. Do you guys see there is A, there is A, there is A? Really, we can cancel that out. We are not going to write it down again. So we just end up with P naught plus rho times G times H minus P equal to 0. Just to make it, to show it, to rearrange and then show it in a simpler form, we can just write P equal to P naught plus rho G H. Okay guys, so this is the equation for finding a pressure at depth H, okay? And then this is also called hydrostatic pressure equation. Hydrostatic pressure equation. I'm just gonna write this, okay? Hydrostatic meaning water. Hydro is water, static means is at rest, right? So this fluid, so pressure at equilibrium, really, when we say hydrostatic pressure, okay? So this is the equation here.